Hi everyone, welcome back for part 2 in our series of motion of charged particles in electric fields. Okay, so just to recap, we're looking at topic 2, which is motion of charged particles in electric fields. And in this presentation, we'll be covering the last two of our dot points for this particular section on electric potential difference. So we're looking at the derivation of an expression involving the electric field strength vector, and also how to solve some problems involving the use of that formula. Alright, so let's go through the derivation of how we actually get this formula. If we have a uniform electric field that has 2 points, x and y, and these points are separated by a certain distance called d. Now, the potential difference between x and y is going to be measured as delta V, or the change in potential difference, and we'll say that y is positive with respect to x. Now, the important thing to note, if we look at this diagram, we've got the electric field lines shown here. So if we have a look at this electric field, we can tell that it would go from positive to negative. So that's an important piece of information to note. Right, now as field is uniform, the electric field strength, or E, is constant in magnitude and direction throughout the entire field. So therefore the force on the charge is going to be exactly the same throughout the field. And we know that through the formula F is equal to charge multiplied by electric field strength. So no matter whereabouts in that diagram each charge is found, it's going to have the same force acting on it. Alright, so as we know from part 1 of this presentation, if we have a charge being moved from any point to another point within an electric field, we know that work has to be done. So the work done is equal to the change in electric potential energy of those 2 points. And basically from the last presentation, we know that the delta EP, or the work done, is equal to Q multiplied by the potential difference. But based on our previous knowledge of work, we can also say that work is equal to the amount of force multiplied by the displacement, or the distance. So we have this equation here. Now we know that force from our last slide was equal to the electric field strength times by the charge. So that gets substituted in here, and we multiply that by the distance that the charges have moved within the field. Alright, so if we now equate those two equations, the Q delta V equation, with our new formula EQD, we can cancel out our Q's from each side and rearrange for D, and what we get left with is a new way to calculate electric field strength vector utilizing the potential difference between the two plates, or the potential difference between the two particular places that the charge is found, and dividing that by the distance that they've actually moved. So it's really handy to know what this would look like if we were actually reading it from a graph. So the slope of a graph of change in voltage over the distance actually gives us the electric field strength. So from our new formula, E is equal to delta V on D, if we actually have a graph of delta V on D, then that would give us the field strength vector. So what this gives us is a really handy formula for actually calculating the electric field strength between two parallel plates. So we have our new formula, E is equal to delta V on D, and in a parallel plate type question, they'll generally give us the voltage difference between the two plates, and also the distance, or how far apart they are. We can compare that to our old version of calculating E, which is force divided by charge. And what we notice is that we now have two alternative units for electric field strength. So utilizing this formula, we have volts per meter, and utilizing our other formula, we have newtons per coulombs. Now, it will depend what type of question you're answering and what kind of information and parameters you're given in the question as to which one of these formulas that you'll actually have to use in a question.